Hi everyone, I'm Ashish Panwar and today I'm excited to talk about Trident, a system that achieves high performance by using all page sizes available on x86 systems. In this talk, we are going to discuss large pages that are essential for dealing with the virtual memory's address translation overheads. x86 systems today support multiple large page sizes, namely 2 MB and 1 GB. While 2 MB pages are used quite extensively today, we find that the hardware resources of 1 GB pages are often underutilized due to inadequate software enablement. In our paper, we first show that 1 GB pages have significant potential to improve performance, and there is no good reason why we should not be using them more often. We have built Trident in Linux, a system that uses all page sizes, transparently and efficiently. We will also take a look at a variant of Trident that optimizes large page management in virtualized systems. This is the age of big data, and the memory demand of applications is continuously increasing. For these applications, TLB misses are quite common, which makes address translation a performance problem. This is because TLB misses are resolved by traversing multi-level page tables that reside in memory. The growth in memory capacity is also leading to deeper page tables that further adds to these overheads. In addition, we have fundamental limitations on how large TLBs can be, because the size of the TLB is directly related to the lookup latency and energy consumption. Combined together, these factors lead to a phenomena that we refer to as the address translation war, where the memory management unit spends a significant fraction of CPU cycles in translating virtual addresses into physical addresses. We can deal with the address translation war with large pages that essentially increase the coverage of TLB, as a result of which we not only get fewer TLB misses but also shorter and faster page table walks. If you look at microarchitectural trends, since their inception about a decade ago, resource allocation for 1 GB pages has been increasing. For example, 1 GB pages had a 4 entry L1 TLB in Sandy Bridge, which has grown to 8 in recent Ice Lake processors. In the L2 TLB, the number of 1 GB page entries has increased from 0 in Sandy Bridge to 1024 in Ice Lake. In fact, in Ice Lake systems, 1 GB and 2 MB pages have the same number of entries. It is therefore quite clear that microarchitects see a huge potential in 1 GB pages. A software ecosystem can use large pages in various ways. For example, Linux provides three methods. Option 1 is a static approach where you relink your application against a library to allocate large pages from a reserved pool of memory. Option 2 is to directly request large pages via mmap family of system calls. And option 3 is an application transparent mechanism where large pages are handled by the kernel itself. A popular example of this is transparent use pages or the THP support of Linux. The first two of these methods have some usability issues. Recompilation is problematic for legacy applications, and memory reservation is problematic for overcommitment in shared infrastructures such as the cloud. In addition, large pages allocated via these methods aren't meant to be broken into smaller pages or to be swapped out of memory, so they preclude fine-grained memory management. The third alternative is quite attractive and offers all the desired features. This is why THP is so popular today. Unfortunately, THP supports only 2 MB pages on x86 systems. So on one hand, we see that the hardware is devoting more and more resources to 1 GB pages, and on the other hand, we find that the software ecosystem has been underutilizing these resources. At this point, it is natural to ask why is it so? We hypothesize three reasons for this. One, there is a lack of evidence on how useful 1 GB pages are to real-world applications, and without a clear evidence, software community has little motivation to improve the support for 1 GB pages. Number two is the fact that software memory management becomes challenging as the page size increases. And number three is the concern about potential TLB thrashing, because historically 1 GB pages had only a few TLB entries. Therefore, applications with poor locality may create a situation where the MMU spends most of its time in replacing TLB entries. We look at all these aspects and try to address them in our paper. First, we analyze 1 GB pages and show that they are extremely valuable. Second, we design and implement Trident to embrace 1 GB pages transparently. And third, with evaluation on a real system, we look for any evidence of TLB thrashing. We analyze the profitability of 1 GB pages over 2 MB pages by allocating them via the static allocation method of Linux, that is huge TLBFS. We analyzed several large memory applications, including key value stores, machine learning, and HPC workloads on a real Skylake machine that has 192 GB memory and 18 cores per socket. The system provides TLB coverage of 6 MB and 3 GB with 4 KB and 2 MB pages, and of 16 GB with 1 GB pages. The graph shows how much performance 2 MB and 1 GB pages improve over the baseline 4 KB pages. The numbers on top of the bars show the difference between 1 GB and 2 MB. The difference, as we can see, is quite substantial, as high as 27% in case of B tree. We do the same analysis for virtualized systems as well, where the cost of a TLB miss is much higher because they use two levels of page tables for address translation. The graph on the right shows that 1 GB pages can be even more valuable under virtualization, where the difference between 1 GB and 2 MB pages is as high as 85% in case of Keneal. Overall, these experiments demonstrate the value of 1 GB pages over what we get with 2 MB pages. Now that we know that 1 GB pages have significant potential, the question is how do we use them? One option is to simply replace 2 MB THP with 1 GB THP in the existing Linux implementation. Unfortunately, this is not the best idea. The reason is that some virtual address regions cannot be mapped with 1 GB pages because they are either not big enough or not aligned at 1 GB boundary. And in some cases, such regions contribute to a lot of TLB misses. For example, these graphs show the address spaces of graph 500 and SVM. The x-axis shows the virtual address space and the y-axis shows the relative TLB miss frequency of each 2 MB region. The regions colored orange cannot be mapped with 1 GB pages because they are not big enough, but their TLB miss frequency is the highest in the whole address space. If we were to replace 2 MB THP with 1 GB THP, these orange colored regions will have to be mapped with 4 KB pages, which would not be ideal for performance. So this means that we should use all large page sizes, not just the largest, even if they provide higher TLB coverage. To realize this systematically, we built Trident in Linux. Trident is basically a set of 3 enhancements over Linux, where the first 2 components deal with extending THP to a more hierarchical structure for supporting multiple large page sizes. We introduced the third component to deal with physical memory fragmentation more efficiently, especially for 1 GB pages. Let's look at these components one by one. The first one is eager large page allocation, where we try to achieve best possible TLB coverage by allocating 1 GB pages at the time of page fault, followed by 2 MB and 4 KB page allocation if required. While this is good for performance, one potential problem arises due to the fact that we need to zero fill a page before it can be allocated to a process. This is a security requirement because otherwise an application's data can leak to other entities. Zero filling a 1 GB page can take hundreds of milliseconds. That adds to the latency of page fault. We avoid this latency by asynchronously zero filling 1 GB pages in the background. This way, 1 GB pages can be allocated much faster. The second component is opportunistic promotion of memory regions to large pages. While we try to allocate 1 GB pages early, some address regions may have to be mapped with 2 MB or 4 KB pages because either the region was not big enough or we could not obtain a 1 GB page frame due to fragmentation. We take care of these situations by promoting regions to large pages in the background. Similar to allocation, here also we try to first promote smaller mappings to 1 GB pages. If not possible, we promote them to 2 MB pages. If required, we do this multiple times so that 1 GB pages can be utilized to their maximum effect. Before we discuss our third component, smart compaction, let's take a quick overview of how Linux compacts physical memory to allocate large pages. Linux maintains 2 pointers, namely source and target. The source points to a range of page frames that it wants to free, and target points to a block where the source block's data can be copied. The source pointer moves from left to right, while the target pointer moves from right to left. We find that this sequential approach is inefficient because it disregards how the physical page frames are allocated. For example, in the picture shown here, Linux would select the leftmost memory block as the source, which would require migrating 3 page frames. At this point, there are 3 better alternatives that require less data movement. The second problem comes from unmovable pages. For example, Linux cannot migrate kernel objects such as page tables and DMA buffers. Linux's approach of compaction also disregards the placement of unmovable data, and it can select a memory block as the source even if the block contains unmovable pages. In the example shown here, Linux would migrate the first page out of the source block. The second page is already free. It is only when the source pointer reaches page 3 that Linux would realize that this block cannot be freed completely. It would then skip this whole block and move over to the next block. Both these scenarios are examples of unnecessary data movement, and it becomes really problematic with 1 GB pages where the amount of data movement can be significantly high. Trident is more prudent in its approach. What we do is, we maintain 2 counters for each 1 GB block. One counter captures the occupancy of the block and the other counts how many unmovable page frames are present within that block. When we want to compact memory, we simply scan this metadata to greedily select the source and target blocks. The source block is the one with least occupancy and no unmovable data, while the target is the one that is most populated but has at least one free page. This way, we copy minimum amount of data possible at any moment. Now let's see how Trident performs, and especially how its different components perform. We compare three variants of Trident with THP. One is Trident 1GB only, where we don't use 2MB pages. Second is Trident NC, where we use both 1GB and 2MB pages but don't use smart compaction. And the third is where all components are used. Clearly, using only 1GB pages is not the best option. We discussed SVM earlier, where we saw that some of its addresses that have high TLB misses cannot be mapped with 1GB pages. If you use only 1GB large page size, it degrades performance for applications like SVM. Clearly, we get better performance when we use 1GB pages in tandem with 2MB pages. Also note that in the absence of fragmentation, Trident and Trident NC perform similarly because compaction is not required. We also study the same configurations under fragmentation. This graph shows that Trident is able to sustain the benefits of 1GB pages even when memory is fragmented. It also shows that all the components of Trident contribute in its performance. We also find that the number of CPU cycles that are spent in page table walks consistently go down with Trident, and there was no evidence of TLB thrashing on our system. Also note that our Skylake system provides only 16GB of TLB coverage with 1GB pages. On Ice Lake systems with much larger coverage, we expect that Trident will perform even better. Next, we discuss how we can optimize Trident further for virtualized systems that involve two layers of memory management. Based on the discussion so far, it is clear that data movement is the dominating kernel activity in the management of large pages, either during large page promotion or while compacting memory. For virtualized systems, we observe that we can mimic data movement with copyless page migration, which can ultimately be used to lower the cost of promotion and compaction. The example shown here is how traditional page migration works. We have two virtual pages v1 and v2 that are mapped to non-contiguous page frames g3 and g5. If the guest OS wants to remap them to two contiguous page frames, for example g1 and g2, it would first unmap v1 and v2. Then it would migrate g3's content to g1 and then migrate g5's content to g2. Finally, it can establish a new mapping from v1 v2 to g1 g2 that is contiguous in GVA to GPA mappings. The example on the right shows how copyless page migration works. Similar to the example on the left, we have v1 and v2 mapping to g3 and g5. In order to map them to contiguous page frames g1 and g2, we first unmap v1 and v2. Then we exchange the page table mappings of g1 and g3 in the host physical address space. This will have the same effect as if the data of g3 has been copied to g1. Next, we can do the same for g2 and g5, which is equivalent to copying g5's content to g2. Finally, we establish a new mapping that is contiguous in GVA to GPA. This way, we made v1 and v2 contiguous with simply manipulating page table pointers. In Tridentpv, we use this idea to optimize both promotion and compaction. For this, we replace data copy operations with hypercalls from guest Linux to KVM. For example, we issue a hypercall with parameters g1, g3 to mimic the effect of copying g3 to g1. And similarly, the next hypercall with parameters g2, g5 mimics the effect of copying g5 to g2. However, if we replace all data copy operations with hypercalls, it creates a performance problem because hypercalls are expensive. They involve VM exits and each one of them can take hundreds of microseconds. We can optimize this by batching multiple requests into a single hypercall. And that is possible because whenever we compact or promote pages, we essentially do a lot of data movement together. So batching works really well. In the best case, we can promote a 1GB page out of 2MB pages with just a single hypercall. This experiment measures the time the guest operating system spends in promoting a 1GB page out of 2MB pages. The effectiveness of our approach is quite visible here. While copy-based promotion takes about 600 milliseconds, Tridentpv reduces it to only 30 milliseconds without batching and further to only half a millisecond with batching. Finally, we evaluate Tridentpv in both fragmented and non-fragmented settings under virtualization. The results show that Tridentpv comfortably beats our baseline THP system in terms of performance. In a non-fragmented system, it improves performance by as much as 47% for Kernel Under fragmentation, the improvement is as high as 24% for GUPS. That completes our discussion of Trident. In this talk, we looked at how the micro-architectural resources of 1 GB pages are being underutilized, even though they have been commercially available for a decade. We analyzed 1 GB pages to investigate their profitability and built Trident in Linux to exploit the synergy of all page sizes. We further optimized large page management for virtualized systems with copyless page migration. Trident comfortably outperforms existing state-of-the-art THP solutions that only focus on 2 MB large pages. Trident is open source and we encourage you to give it a try. For more details, please refer to the full paper and reach out to us.